I find it exciting that when somebody comes in and they are really excited about getting a chance to get out and climb one of the mountains that I've climbed or backpack in an area that I've backpacked, and they're looking for the right piece of equipment to get out there and do it. There are times when I've been researching things on the internet and I get overwhelmed, and sometimes it's just nice to sit down and talk with one person one-on-one. That's why I think that customers come to us, is because we are local, and the gear that we carry is the gear that we ourselves like to use. So if you hike, climb, or ski in the Pacific Northwest, it'd be awesome to have you come in here so we can get you all geared up to get outside.
All right, next up we have NWAC's very own Peter Moore, an avalanche forecaster out of the Mount Hood area. Peter is in his second year as an avalanche forecaster for NWAC and has a background as a mountain guide and ski patroller. He is a full-time resident of Hood River, Oregon, and primarily focuses on the Mount Hood and East-South Washington areas. Peter's role with NWAC is significant, as he became the first field-based avalanche forecaster from the Mount Hood area, and dramatically improved our ability to understand that unique snowpack, as well as connect with our Oregon community. Everyone who has spent time touring in the Pacific Northwest has noticed that volcano skiing, for better or for worse, can act a lot differently than other peaks in the Cascade Range. In this talk, Peter will address some of those differences and how we can prepare for them. Peter, I'll pass it over to you.
Thank you. All right, so we're talking about unique snow and avalanche conditions of the Cascade Volcanoes. We've got a couple of them here in the Northwest. Starting from outer space, looking down, we can see the Northwest here. And if you have decent resolution on your computer screen or TV, you can see a couple little dots of snow that stand out in Washington there near that arrow. And you can also notice the proximity of the Pacific Ocean, the Gulf of Alaska, the tropical Pacific, and the continent of North America, mostly up in Canada, nearer to the Arctic. Those are things that are going to come into play with some of the unique conditions in the Northwest volcanoes. So zooming in a little bit, you can see the Washington Cascades, the southern volcanoes, and northern Oregon. Those especially stand out. Mount Baker and Mount Glacier get kind of obscured by some other mountains in the range there, but here they are circled. And one thing to note here is the elevations that are listed to the right. Almost everything's over 10,000 feet, except for Mount St. Helens, which used to be over 10,000 feet. And this next slide, this is sort of a Google Earth from almost ocean level. This is the southern volcanoes, so Mount Rainier, Mount Adams, Mount Hood, and Mount St. Helens. You can see pretty clearly that these are, there are no other mountains around them. There's not a lot of terrain that's anywhere near as high. Again, Baker and Glacier get a little bit more occluded with some other terrain in there, but these southern volcanoes especially, they have nothing blocking them from the ocean. And that's probably fairly intuitive for a lot of people, but it's a major factor in the weather and snow conditions that happen on these peaks. So we know that they're taller than everything else. They're closer to the ocean. That's another thing that we see. And like I said, storms can reach these volcanoes pretty much unimpeded by any other land or mountains. And that increases the ability of a storm to deliver that weather to the mountain. And like I said, we're also in a position where we can receive weather events from both the Gulf of Alaska and the tropical Pacific. So there's kind of a weather pattern that we might see coming from the Gulf of Alaska, low pressure. It's cooler, moist air coming from the northern Pacific. And the way that that low spins, we bring this southwest flow into Washington and Oregon. And I think that's pretty well known that Washington and Oregon see this classic southwest flow. And this is going to drive the weather to the southwest slopes of all these mountains. And we'll talk about that. That's going to be kind of a driving factor for a lot of the weather that we get. But that's one way that we get our weather. Another thing is that we're fairly close to the rest of the northern continent. We're pretty far north, and we get this cold seeping out. So in this image, you can see kind of the pink and purple colors that are really, really cold, and the blue that's pretty darn cold, and the green is not quite so bad. But in this instance, the really cold air is seeping out of the central Canada into the northwest, and that can influence our volcanoes as well, especially since they're taller than everything else as well. So they're receiving maybe even more cold air than this image shows. And then here's another setup. So we already talked about getting weather spinning to the southwest out of the Gulf of Alaska, bringing us kind of cooler but still moist air. That means snow, essentially. In this case, this is an atmospheric river coming out of sort of the tropical Pacific, that blue line being the highest intensity of precipitation. But this is from September this year, actually. So we weren't really getting a lot of snow in the mountains, but we got quite a bit of precipitation during this event. And this is referred to oftentimes as a pineapple express, especially during the winter. We often get rising temperatures, lots of precipitation. I mean, this is just kind of a funnel out of the warm, wet air from the southern part of the Pacific Ocean, southern part of the northern hemisphere anyways. And this is definitely a common occurrence, not every day, but several times a winter. And this type of event comes with rising freezing levels and oftentimes rain up to tree line or above. But one specific thing that we see on the mountains or in the volcanoes is that if there's already cold air in place, like we saw from a couple slides ago, cold air from the continent, if there's already cold air in place when this sort of weather pattern sets up, it really sets us up for maybe the biggest storms as far as snowfall, because that cold air or that wet air is coming over the cold air. And here's an image of a warm front. And you can see kind of the way that warm front moves over cold air. It comes in at this angle, right? So the warm air is rising. And as that cold front approaches, we get quite a bit of rain or snow, especially at higher elevations. And that warm air hasn't quite made it all the way in to totally inundate the area. And I think this is a very common setup that we see on the volcanoes is that we have cool air or cold air, a warm front approaches, it snows quite a bit, and then at the end of the storm, the freezing levels rise, the skiing gets not quite as good, or maybe it even turns to rain, especially at the pass levels, that kind of thing. The highest elevations of the volcanoes are going to probably remain snow in most cases, but this sort of weather pattern of cold air in place with the warm front and heavy precipitation coming out of the tropics is, I think, pretty common to the volcanoes. And so this is one of our biggest producers of heavy snowfall, but it's also one of the biggest producers of high avalanche danger, where we have a significant snow event with rapidly rising temperatures and possibly rain at the end of that snow event. So here's a headline from, I think this is from Snowbrains, January 2018. It says Mount Baker ski area, Washington will be closed Sunday and Monday due to rain and avalanche danger. So I poked into the weather data, and the week prior to this event, Mount Baker received over 50 inches. It's a little hard to go back super far in the time frame there, but they received 50, 60 inches of snow in the 4 or 5 days prior to this warming event, and then got 5 inches of rain. So Mount Baker closed for a couple of days. We've probably all seen this type of event, whether you ski at Mount Baker or not. We've all experienced those days where it's been really good for a couple days, and then it gets warm and heavy, or it rains. And that's kind of what's going on, and is that moisture is coming out of the southern part of the Pacific, or the freezing level. Even if it's not coming out of the southern part of the Pacific, the freezing levels are rising with that warm front crossing over the mountain range. And this is a very common setup in the Cascades. And this is sort of the opposite setup, same website, Snowbrains. We've probably all seen something similar to this. It says, you know, Mount Baker forecast for 122 to 181 inches of snow in 4 days. It's sort of hard to comprehend that amount of snow, I think. And the question is, you know, as a skier, when you think Mount Baker, you think of maybe the ski area or the accessible touring terrain from the roads. And unfortunately, this is a bit of a novelty headline. The mountain is capable of receiving that kind of snow, but did it actually snow 181 inches in 4 days? Again, going back in time is a little bit challenging, but this is from 2017, and it's in October, which is quite early. So the freezing levels really fluctuated. And, you know, there's no weather station at the top of Mount Baker. So at the ski area, it looks like they received about 5 to 10 inches of snow, but they received 11 inches of precipitation, which is huge. Again, this is in October, so the freezing levels fluctuated. That forecast that the headline resulted from was using a 10,000 foot elevation. So of course, everything's going to be snow at that elevation in October. And it's a little bit overdone. But it's clear that the mountains, especially the volcanoes, with their elevation and their proximity to the ocean, they're capable of creating storms like this. And Mount Rainier has a world record for snowfall. This is for an entire calendar year, so over 1,200 inches of snow between February and February, 71 to 72. That's 680 inches on the ground at Paradise. And Mount Baker, 1,100 inches in 98, 99. I think that's just during the ski season. That's 530 inches on the ground. We know that these Pacific Northwest volcanoes can receive that amount of snow, even if that one example of 181 inches didn't come through in October in 2017. One thing that makes the volcanoes snow so much is the wind. Again, you know, being close to the ocean and not having a lot of terrain in front of them, they're definitely subject to more moisture and more wind coming off of the ocean. And then this orographic lifting is a major factor. So I think the diagram does a pretty good job of showing it here. As the wind comes from the ocean, it's full of moisture. It rises up the terrain. You know, it hits these volcanoes and has to go up. So it cools off as it rises up, and that moisture condenses and precipitates. It's cold enough to be snow at the upper elevations, so it snows heavily, especially on our southwest slopes of our volcanoes, because that is generally the wind direction that we're getting, whether it's from the tropics or whether it's from the Gulf of Alaska. We're seeing the most precipitation on the southwest slopes, because that's generally where we have our wind direction driving this moisture. And then on the leeward side of the mountains, it dries out. So you see that in the entire Cascade Range. The east side's drier and cooler than the west side, getting more orographic effect. But I think a particular example of this is really clear, where Paradise and Mount Rainier on the southwest side or south side see huge amounts of snow, and oftentimes Crystal Mountain, which is essentially, you know, it's very close to Mount Rainier, it's almost on it. Paradise might see significantly more snow than Crystal sees, because of this orographic effect, where the wind is driving up Mount Rainier, it's snowing heavily, and then as that wind comes over Mount Rainier or around it, it's drying out, and Crystal on the northeast side doesn't see quite as much snow. And they're still getting snow, but the air is drying out as it descends, as you can see in the picture. And this is not just true of Mount Rainier. This is true of all the volcanoes. And you know, a little bit of it depends on which direction the particular storm track is taking, but it's very common that the south and west slopes of the volcanoes see significantly more snowfall than nearby terrain. So all these, basically every weather event comes with wind. That's what moves weather around the world. And wind transport is a huge factor for snow accumulation. It's something we think a lot about in the avalanche world, wind slab formation, and you know, how much snow is being moved around. So this is a picture from Mount Hood back in my ski patrol days there. This is just going straight to the picture, this is about a 2-day storm before we did avalanche control. This is explosively triggered, not ski triggered, but you know, you can see that this is not a cornice. This has been so heavily controlled that in this picture you're seeing basically an avalanche that is not a cornice fall event, and that's taller than the person standing there. And this is a particularly big one. This is probably 1,000 feet wide, or maybe 800 feet wide, with an average crown height of about 2 to 3 feet. This person is standing on the biggest portion of it. But the wind can rapidly transport and redistribute snow. Moderate to strong winds can double or quadruple the rate of snow accumulation on lee slopes and scour some of these windward slopes, windward being the side that is receiving the wind, and lee being the side that's, you know, the wind is going towards, or going, it's dropping all the snow there. If the winds get stronger than, say, moderate to strong, they can actually take the snow into the air and basically never let it come back down to earth, and it can evaporate, so to speak. I think technically it's sublimate because it's a solid going to a gas, but If the winds get really, really strong, which we do see on these volcanoes, again, because they're so close to the ocean and uninhibited by any terrain west of them, it can actually take away the snow. So, for example, Mount Rainier, the tallest of the volcanoes, oftentimes doesn't accumulate quite as much snow as you'd think on the upper mountain during the winter relative to how much snow Paradise accumulates. You know, Paradise has basically a world record for snow accumulation, but the upper mountain, and I'm speaking here with my a decade of guiding experience on Mount Rainier, showing up in May, looking at the upper mountain, wow, all these crevasses are still open. Come, you know, middle of May and June, it's dumping snow and it's filling in the upper mountain in a way that it didn't do during the winter. And that's, I think a lot of that is from the colder temperatures, the stronger winds, blowing away a lot of the snow accumulating at those upper elevations, where Paradise is got more moderate temperatures, a little bit less strong winds, and it's really stacking up snow during the winter. So those are some very kind of unique features that we don't, or unique weather occurrences that we don't really see in some of the regular peaks of the Cascades. Hopefully you can all see this. This is a time lapse that I took earlier this year. I'll play it again. This is touring on the north side of Mount Hood. And this is a very windy day. It provides a couple examples. You can see in high speed the snow transport in the foreground. You can see the orographic effect of these clouds coming over the summit. So the cold air is being pushed up the mountain. It's condensing and forming that little cloud, even though the day is generally sunny and nice. And then also in the sort of center left here at tree line, you can see the snow being blown into the air and just driven off the mountain. That snow is in turbulent suspension, and it's probably never going to land anywhere. It's just going to sublimate into gas or evaporate, or however you like to think about it. It's actually windy enough to kind of knock that guy out of balance as he's skinning. And so here's just a still from the photo. In the foreground, you can see the snow being blown across the foreground. You can see I'm repeating myself, but again, you can see the cloud cap coming across the summit. And you can see that in the left side of the photo off of the Cooper Spur, if you're familiar with Mount Hood, you can see that snow in turbulent suspension, probably several hundred feet into the air on that left skyline in the photo. On this day, I think I went back and looked at the forecast. The winds were at 5,000 feet, NWAC forecasts, west-northwest 25 to 35, and 9,000 feet. I have to move my little zoom thing here. 9,000 feet northwest, 50 to 60 mile an hour winds. In reality, you know, these are free air forecast winds. In reality, I think the winds that day were far stronger than what was forecast. And part of that is because of the topography of the mountain, really channeling the winds. So with any wind that I wrote here, Mount Hood east winds, but with any wind that has a north or an east component at all, Mount Hood in particular sees extremely strong winds that really scour a lot of the normal avalanche slopes that we have. So we're typically subject to, at Mount Hood, frequent southwest winds and weather patterns, and most of our large and frequent avalanche paths are north and east facing. And so whenever there's a north or east wind, in this case it was northwest, but that north component really funnels the wind around the mountain and accelerates it very strongly, and it actually scours a lot of our typical avalanche paths. And so in that case, the winds were maybe they were pretty strong, but 25 to 35 at 5,000 feet is not extreme or anything. And I think the wind was behaving in an extreme way during that period. And then finally, these are pictures from Mount Hood, just because I'm down here, and I think all these pictures are from my patrol days at Mount Hood Meadows. But this is some avalanche debris from, I think, 2 different artillery triggered slides that came into the ski area. It's pretty likely that these would have happened naturally if we did not trigger them. But this is, all of the volcanoes are subject to this. They have a lot of large scale avalanche paths. They have a lot of terrain above tree line, and some pretty significant avalanche paths that can accumulate a lot of snow. So if you look carefully, there's a couple patrollers in that photo, and here's a few different photos. A photo on the left is this large slide kind of banking a turn in a gully and some people climbing on it. The photo in the center is the Newton head wall. There's a crown in the center of it that's probably 10 or 15 feet high. This is looking through a spotting scope from over a mile away. And the photo on the right is actually a pretty small slide, probably a D 2.5 or 3, but you can see that you can see the path that it runs, and you can see some of the terrain above. So if a much larger slide were to happen at that higher elevation, it's got a lot of snow to entrain below, and I think that's one of the particularly unusual things about these volcanoes. The slide path here on the right side of the photo, if that were to originate nearer to the top of the mountain, like in the center photo, it can run well over a mile in length, and that's a lot of snow to accumulate as something slides. And so this is a different event. I don't remember the year actually, but you can see kind of the wet debris. It wasn't a wet slide to begin with, but it became a wet slide at the lower elevations, and the power that it has on the right photo, especially, you can see these trees just kind of sheared in half, these smaller trees just sheared in half into that wall as the debris is flowing. So we have, I probably should have made a conclusion slide, but we have kind of the proximity to the ocean, the height of these volcanoes, the ability to receive storms from both the Gulf and the tropical Pacific, the Gulf of Alaska and the tropical Pacific, and then the fact that there's a lot of big terrain above tree line that lends itself to being potential avalanche paths that we don't see on some of the smaller mountains in the Northwest. And that's about all I have right now.
Thank you so much, Peter. That was great. Just a quick update that our presenter Laura is having some technical difficulties on her end. So we are going to move from Peter's talk on to the anti-racism panel at 6:10. And then her talk will follow that anti-racism panel, and all of the video from that will be released later, or you're welcome to stay on and watch that. So Peter, I'm gonna check in on the Q&A here and see if we have some questions from the audience. Rainey Hoffman asks, what's the best source for assessing volcano risk? I.e., does NWAC have a separate volcano forecast, or should we just extrapolate from the high altitude portion of the regular NWAC forecast?
Well, keep in mind that, you know, if you're near Mount Hood, a lot of the information is coming from Mount Hood. If you're looking in the west-south forecast zone, a lot of that information is coming from Paradise. And likewise in the north and west zone, a lot of that information is coming from Baker. So if you're thinking about the tippy tops of these mountains, we're not getting very good information during the winter. We don't provide a forecast at the uppermost elevations, but you know, nearer to the access points for these peaks, we're getting pretty good information and providing forecasts within that zone. And since that's a major part of our access to those mountains, those trailheads are getting covered really well in our forecasts for the particular zone.
Got it. Thanks, Peter. One question that I hear coming up a lot from folks in our community is around what they do before our forecast starts and after it ends. And I think that that relates a lot to travel on volcanoes. I know that last weekend, a lot of people were headed out, and then in the springtime after we stopped forecasting, what resources would you recommend for people heading into the mountains before we've got a forecast?
Yeah, I think it a little bit of it depends on whether it's fall or spring. In the spring, I'm particularly interested in the freezing levels, especially if we haven't had recent snow, how fast things are thawing out, and whether or not we're going to be looking at kind of the wet loose problems. In the fall, I'm particularly concerned about snow coverage and not breaking my shins on some hidden rocks. But keep in mind that all year round, our telemetry works on the website, so we can, even if NWAC's not publishing a weather forecast, we can go and see you know, how cold it was and how much it snowed, which direction the wind was coming from, and how strong the wind was. And those are really, really powerful tools to be able to create your own forecast. And it takes some practice, but all the information is there.
Yeah, I think that that's a good point, and also gives you good practice for using those same tools when we are forecasting to confirm or deny what you're seeing in the forecast. Absolutely. Yeah, do we have any other questions from those in the audience, specifically around forecasting? Charlie Rubin asked, does the UW Atmospheric Science use NWAC telemetry OBS from the 4 different elevations?
I don't believe that the forecast models that the UW puts out use our telemetry data. I know that there have been some independent forecasters trying to do some AI learning that uses input like that, but I don't think that the GFS models from the UW are using our data, although that might be a better question for Dennis or Robert. Great. Yeah, Charlie, if you want to follow up with us, we can direct that question to one of the meteorologists on our team. Great. A couple more questions here. Peter, can you speak to, as a forecaster, do you feel like it's much more challenging to forecast for a volcano over some of the other regions you cover, or when you forecast for other areas in the Cascades? That's a great question. In some ways, I think it's easier to forecast for the volcano because I live on it, and I go to it every day. So when I sub in on the west-south zone, you know, I haven't been skiing at Mount Rainier and I haven't been skiing at Crystal, and that's a real challenge. But more to your point of the question is probably there are some real challenges to it where the weather and snowfall can be extremely different on the south or the west side of the mountain than on the north or the east side of the mountain. So I try to forecast based on access and ease of access, where I'm spending most of my time looking at the places that people can ski given a day, and not travel to the places that it takes a whole day to skin in to go ski. So in some ways it's easier, in some ways it's harder. There's a lot of variability, but for example, at Mount Hood, the whole forecast zone is quite a bit smaller than some of the other regions. You see a lot of discrepancy in, say, the west-south zone, where you've got some really low terrain, and then you've got Mount Rainier, the highest, you know, nearly the highest peak in the 48 states. There's some very different stuff going on when you get to the volcanoes. So it can throw it off, but I think that there's a way to approach it where you can sort of forecast more for your access area and your intended goal rather than for the mountain as a whole. And I think that's what a lot of us forecasters are doing, is trying to concentrate our information gathering to the specific places that most people are going.
Great. Thank you so much, Peter.
Thank you.
Yeah, have a great night.